Hello everyone. In the previous lecture, we had uh, discussed some introductory statements regarding the 3D elasticity chapter, and in the process of doing that, we had mentioned that uh, we intend to ultimately take up the famous, historically important Kelvin's problem. Now, uh, in order to do that, what we'll do is first introduce the displacement, the mathematical technicalities of the displacement potential method. Now, within this method, there are a number of different ways in which the displacement vector can be expressed in terms of the potentials. Okay, so the idea is this, that if I directly go into the solution of the Kelvin's problem, okay, the method or the particular way that I have to take up, if I directly present that, it will appear to you like some kind of black magic. Okay, so I mean, without any motivation or without the preliminary steps behind that kind of a representation, which will actually end up using there, you will be completely lost. Okay, so the idea here is that we are first going to discuss some general things and slowly build up to a stage where we'll be able to write down the kind of displacement potential which will be useful for the Kelvin's problem. Okay, so as the very first step towards that, we note something directly from mathematics, which is called the Helmholtz representation theorem. Okay. The Helmholtz representation theorem, it basically gives us a recipe of expressing a vector just like a displacement vector, but it is more general than that, of course, because it's a mathematical theorem. It gives us a recipe of expressing a vector in terms of potentials. And what it says, so we are going to present this theorem without any proof. It's not that long, that proof is not that long, but I mean, in the interest of keeping things relevant directly for applied elasticity, we are not going to go into that. What it says is that any sufficiently smooth vector field, okay, any sufficiently smooth vector field can be represented as the sum of the gradient of a scalar potential and the curl of a vector potential. So this part, any sufficiently smooth vector field, that is basically giving us an indication that it should be properly differentiable. Uh, so sum of the gradient, okay, sum of the gradient of a scalar potential and the curl of a vector potential. Okay, so what is this telling us in terms of the displacement vector? What we obtain from this Helmholtz representation theorem for our displacement vector? So when we have this displacement vector, what this Helmholtz representation theorem is telling us is that this general displacement vector, no matter which problem we are taking up, this can be represented as some grad of phi, where this phi is the scalar potential and the curl of a vector potential. Please note that this phi is a scalar potential. This omega, uh, this omega vector, that is a vector potential. Okay, so let me write this here. So phi is the scalar potential, and omega, that's the vector potential. Now you may think that what is this? Because on the left hand side we have these three unknowns, the ux, uy, uz in a rectangular Cartesian coordinate system, and now on the right hand side we have basically four unknowns, because this phi is unknown and the three components of this capital omega vector, they are the unknowns. So are we trying to make our life easier or harder? Well, we'll see what are the consequences of, of using this kind of a representation, and we can draw our conclusions from that. All right. So first a little bit of discussion about the properties of this kind of a representation. So first of all, you note that this part, the grad of phi, this is what is referred to as the irrotational part. This is the irrotational part of the u vector. And what is the meaning of this irrotational part? It basically just means that if you take the curl just of this part, if you take the curl of this part, then this is 0. Please note that this is not an assumption or a requirement. This is true identically. So if you have any scalar potential, you take the grad of that and then you take the curl of that, this is going to be true. This is going to be 0 identically. This part, this is referred to as the solenoidal part. The name solenoidal, it is basically taken from its link with electrostatics. What it is basically telling us is that it is divergence free. Divergence free means if you take the divergence of that part, okay, so you note that this capital omega vector is a vector. You take the curl of that, that also is a vector. Okay, so overall this is a vector. So if you have any vector and you say that a vector is solenoidal, it basically means that if you take the divergence of that vector, it is 0. Okay, that's it. So again, you note that this is identically true, and you can take this up as a little exercise for yourself. Consider a general omega in the rectangular Cartesian coordinate system, for example, with components omega x, omega y, and omega z. Take the curl of that and finally take the divergence of that result. You'll see that it identically comes out to be 0. You can do this yourself. Okay, we are not going to invest any time on that. Now, what are the consequences of this? When we consider this displacement field through this rather complicated looking representation, it is fine that the mathematical theorem is telling us that this can be done, but so what? Okay, it can be done, all right, fine, it looks nice, very mathematical, but what is the use of this? Okay, so in order to understand the use of this, we have to actually try to connect this with what we had been discussing in the previous lecture at the very end. So please note that our ultimate goal here is to represent this stress equilibrium equation in terms of the displacement, and then to express that displacement or that second order differential equation in displacements in terms of this potential, and to see what kind of things we can deduce from that. Okay, now if we actually do these steps, that that we substitute the linear elastic isotropic material behavior for the sigma in terms of the strains, and then express the strains in terms of the displacements using the, uh, the strain displacement relations, then the differential equation that we are going to obtain is basically this. Okay, so you see, so what I'm trying to do here is this: delta dot sigma plus 2b here equal to 0. From that, we are going to, I don't need this arrow, so this is a separate thing that I'm writing here. Okay, so from here what I will obtain is delta dot u, the grad of this whole thing, plus g. All right, now you see what I have here. I actually have my this displacement vector, and I can take the divergence of that. I will obtain some expression using in terms of this phi and capital omega. What about this del squared u? Well, it turns out that directly taking the Laplacian doesn't do me much good here. Okay, so what I will do is to uh, use a vector identity to transform this Laplacian of u, this del squared u, uh, into something else. Okay, and you'll see that that's something else which will actually be involving the curl of u, uh, and we can actually we can utilize some simplifications involving these things. So in order to avoid jumping between these expressions and these expressions, what I will do is I will first keep two results in my hand ready. First of all, I will take the divergence of this u vector, and then I will take the curl of this u vector and keep those two results ready in my hand. And then I'll come back to this equation and utilize those results. So this is the plan. So let's go forward with this plan. So we write this u, grad of phi plus curl of omega. Before launching into the actual details of this, let me just point out that within this chapter, okay, so all throughout our applied elasticity discussions, starting in September, many of the discussions have been quite mathematical in nature, and uh, and the level of mathematics that will be utilized in this 3D elasticity chapter, I think it is the highest. Okay, as it is befitting the last chapter that we are going to discuss. So, so please brace yourself. It's not mind-bogglingly difficult, but you have to be a little bit careful here. Okay, so with this preamble, let us start with the details. So divergence of u, so this. Now please note that we have already mentioned that this part is solenoidal. Okay, it is divergence free. So this part, of course, it is 0. So this is quite nice. Okay, now what about the curl? So we have this. All right, Again, you note that we had already mentioned that this grad of phi is irrotational, which means the curl of that is 0. And that is exactly what we're doing here. We're taking the curl of the grad of phi, and this is 0. So immediately this becomes the curl of omega. Now I don't want to leave it like this. Okay, so this is the part where I have to first use my vector identity. And this is the same vector identity which I was referring a little while ago. Okay, so you'll see that we'll have to use this vector identity a few times. So what is this vector identity? So you can actually verify for this yourself that what I'm going to write next is actually true. So we use this particular vector identity, which tells us that the curl of a vector. Please note that this is a general vector identity, not just confined to this omega vector, but I am of course going to apply this now on this omega vector, which is why I'm writing it like this. So this vector identity tells us that the curl of a vector, that is equal to the gradient of the divergence of that vector minus the Laplacian of that vector. Now this seems like a rather hard thing to remember. Okay, now I mean, you can kind of remember it through words, and what you can think of it is like the curl. Okay, so the curl operating on the curl is equal to the grad div. So this is divergence, that div represents the divergence. So it is the gradient of the divergence minus the div grad. Why is it div grad? Because you see this Laplacian, okay, the Laplacian is basically equivalent to the divergence of the grad of this. Okay, so this is the grad, you take the divergence of that, so divergence of grad is the Laplacian. So curl is equal to grad div minus div grad. So it is just an easy way to remember it by words. All right. So if you use this thing, what does it give us? So you see, just written by itself, it really doesn't help us. Okay, so we have this vector identity. If we just substitute here, you get, instead of one term, you get two terms. So what good does it do us? Well, what we are going to do is directly do with the first method of learning this displacement potential. Okay, so all this while what we have been writing is something very general, and now we are boiling it down to something very specific, which is the Helmholtz displacement potential. And what we say in this particular way of displacement potential, the Helmholtz displacement potential, is that we consider the divergence of this omega to be equal to 0. Okay, this is very, very important. So you take this, we take the divergence of the omega vector to be equal to 0. Okay, do not forget this. So if we have this, then the curl of the omega vector, it simply reduces to minus Laplacian of omega, which means that the curl of the displacement vector is minus Laplacian of omega. Okay, so what we have in our hand now is an expression for the divergence. Okay, so this is what it is, this thing, and we also have this thing. So now what we are going to do is to take up this previous equation here, but before I do that, I notice that there is a missing term here. This rho b is missing, so I'll have to make a correction for that. Sorry about that. So rho b is equal to 0. I'm going to use this equation. I'll directly take it from here. Now note that I have this del square u vector here. Okay, so again, by using the same vector identity that I had used in the previous page, this time written in terms of the u vector, I have the curl of u equal to the grad or the gradient of the divergence of u minus the divergence of the gradient of u, which is basically the Laplacian of u. So which means that I basically have Laplacian of u is equal to grad of the divergence of u minus the curl of u. So if I substitute this expression back here, what I obtain just substituting this here, g grad divergence of u minus g curl of u plus rho b is equal to 0. And of course you see that this is the same term which is sitting here, so we can take that common. So we have lambda plus twice g grad of the divergence of u minus g curl of u. And now in this particular equation we have the divergence of u and as well as the curl of u. And please note that in the previous page here I had already obtained these two expressions. The divergence of u was the Laplacian of phi and the curl of u was the Laplacian of omega. Okay, so I'll use that here. So lambda plus twice g grad Laplacian of phi. So this is minus g curl of u. Now curl of u is the minus of the Laplacian of omega. So minus and minus becomes a plus. So this becomes g curl of the Laplacian of omega vector plus rho b. Alright, so now that we have this equation in terms of the potential functions, one may easily question that or one may naturally question that what is the use of this, because as written it does seem more complicated than the original equation. So how does this help us in actually solving the problem if we are making our life more difficult than it already was originally? Okay, and that's an absolutely valid point. So and to really appreciate it, please note that suppose you were supplied with a certain rho b vector, how do you actually obtain the three unknowns omega, the three components of the omega vector and this scalar potential phi? It's actually difficult. However, if you consider a special case, okay, even more special than this, that rho b, okay, so consider rho b equal to 0. Okay, so this is a very special case. When you have rho b equal to 0, you'll see that certain simplifications are possible, and then we'll be able to appreciate the benefit of going down this route. Okay, but at the same time, let us not forget that that we have already assumed this, that the divergence of omega vector is equal to 0. So, so the equation that we are going to work with from now on is this. Lambda plus twice g grad of the Laplacian of phi plus g curl of the Laplacian of omega is equal to 0. Now suppose on this equation, so now our objective is to make some simplification so that we'll be able to actually use or to solve for this. Okay, so you take the divergence of this. So what happens then? So we are considering this lambda and g to be constants. So if we take the Laplacian of or the divergence of this, we have divergence operating on this grad, and here we have this thing. So first of all, you note that despite the complicated looking structure here, you can think or perhaps you can expect that these operators, they commute among themselves. Okay, so I shouldn't be saying commute among themselves, but at least what you can see here is that this divergence, which is sitting completely outside, that will be ultimately operating on this thing. Okay, and we have already seen that divergence of the omega that is considered to be equal to 0. So this entire term goes to 0. Okay, so I suggest that you actually try to prove this thing, that the way that this thing is written, it can be equivalently written as the curl of the Laplacian of the divergence of omega. Okay, so basically what I'm saying is that you can take this divergence operator inside here so that it operates directly on this omega vector. Okay, so this entire term is 0 since divergence of omega is equal to 0. So what we are left with from here, of course I have this lambda plus twice g here, I ultimately have that the Laplacian of the Laplacian of phi, that is equal to 0, which basically means that I have the biharmonic of phi is equal to 0. This is an important statement. Okay, and this gives you an idea that okay, now this is somewhat we can attempt to solve this thing. But what about the omega? That is still left. Okay, you know that we have managed to obtain something for phi, but what about this omega? For that, let us try to take the curl of this thing. Okay, to take the curl. So let's say this equation is hash, to take the divergence of hash here, and now take the curl of hash. So this is lambda plus twice g curl of the gradient of this thing plus g curl of this entire thing. First of all, you note that this phi is a scalar. The Laplacian of phi is a scalar. So this is basically the gradient of a scalar, and we already know that the curl of the gradient of a scalar is identically 0. So in the next step, all that you have to worry about is this thing. Now please note that this is again in the form curl of a vector. Why is it a vector? Because you see omega vector, of course, is a vector, and the Laplacian of a vector is again a vector. So this is basically the curl of a vector. And the moment we realize that, we can again go on and use our vector identity on this particular thing. So we are going to use the vector identity on this. So this becomes basically, so curl of a vector is basically the gradient of the divergence of that vector, the vector that we are considering is the Laplacian of omega vector, minus the divergence of the grad of that vector, so which is basically the Laplacian of that vector. That vector is the Laplacian of omega vector. Okay, and again you note that this divergence, it is going to operate on this, so that is going to be equal to 0. So ultimately what we have from here is that the biharmonic of omega vector is equal to 0. So earlier we had obtained that the biharmonic of phi is equal to 0. Now we are obtaining that the biharmonic of omega is equal to 0, and these are these two equations are so #1 and #2. These are the two important simplifications which we obtain. Very carefully note that we obtain these things under the consideration that, first of all, the divergence of omega vector has to be equal to 0. Furthermore, the body forces have to be 0. And only then the general Helmholtz representation of the displacement vector in terms of a scalar potential and a vector potential, they give us these kinds of simplifications, and we can actually try to solve for this. Okay, so this kind of a representation is good, but as you see, they suffer from certain kinds of restrictions. Okay, notably that first of, I mean, you can do this only if the body forces are 0. So the thing that we are going to consider next, we'll see that how we can perhaps move up a step from this kind of a representation to something slightly different, but which has historically been quite widely used. All right, so on that note, I'll end this lecture. So before just ending, I'll make a note that all of these discussions, as I had pointed out earlier, is basically to provide a step-by-step approach to ultimately something which will develop or what will present towards the solution of the Kelvin's problem. All right, thank you very much.